Okay, folks, we're moving on. If you have your telephone, put it away. Say, phone, I'm not going to let you um, hinder my learning. Okay, exponential decay. Exponential growth we see when we're talking about population growth or cell growth. Um, and exponential growth will also be in the growth of money. Exponential decay is a lot smaller, I'd say. So exponential decay, we're generally talking about the decay of radioactive material. Okay, so when we're talking about radioactive material, you've got a lot of it, right? And it decays. It basically what that means is the atoms um, sort of break apart. Okay, as they release energy, they're breaking apart, and so we're looking at how much of those atoms have released their energy. And so we use a term called half-life. Okay, this is just something that the scientists have chosen as a good measure. They could have used 1/3 life or 1/4 life, but half life makes most sense for, I guess, scientists or math modelists or whatever. So a half life is looking how long does it take for the original amount to decrease to half of its size. Okay, so if I were thinking about this class, let's say I made this course ridiculously hard and I started off with 30 students and students were just like dropping like flies. I would I would be measuring how long would it take for 15 students to drop the course. That would be the half-life of the decay of this class, right? Luckily we don't do that. So we're looking at radioactive material. Another thing we're looking at is drugs. So when you take in drugs, they are slow release or fast release. And so let's say you swallow a pill, okay, some antibiotics or something, and it slowly comes apart. Your stomach digests it and sends the drug all over your body, and your body uses it. Well, medical scientists will look at the half life of that drug. How long does it take for your body to use half of that drug? And then sweat it out, pee it out, spit it out, whatever, right? So the term we're looking at today is called half life. How long does it take for half of the original material to decay, go away? Okay. We could also look at the decay of food, of organic matter, and see the half life of that. We could look at the half life of garbage, inorganic matter like plastic, right? How long does it take for a plastic bottle, for half of a plastic bottle to decompose? That would be a very long half life. Okay? So let's look at that. So first of all, what we saw here is in yesterday's lesson we looked at exponential growth. Let's just remind ourselves of this equation. For exponential growth, this equation solves for the amount remaining at time t, or the amount that something has grown. And we look at the original amount and we multiply it by a base of 2. And that's dt to the power of d. And this 2 represents the doubling. Okay, how long does it take something to double? Now, this graph is actually y equals 2 to the power of x. And that's what we use generally for exponential growth. Now, if I give it a horizontal reflection, my graph goes from an increasing graph to a decreasing graph. And that one flip of a horizontal reflection gives us the exponential decay. So what will be the base of this graph? So it's symmetrical, but it's reciprocal, right? The base is a reciprocal, but the graph itself is symmetrical. Like if you were to fold it on top of itself, it would be increasing and decreasing at the same rate. So when we look at exponential decay, it's modeled similarly. So here's our equation for exponential decay. A of t is amount after elapsed time, or amount after a given time, same as before. I also want to remind students that if it's better for you to just sit and watch me teach and not take notes, no judgment. You don't need to take notes. You can print out my notes later. Okay. A naught, what does that stand for? Initial amount, sure, better than original. Initial amount. And we still call it A naught. Okay, now we see the base is 1/2, and that's because we're looking at a model that is halving the amount. The T up top stands for time that has gone by, or time elapsed. Čas, že minul. And the H is the amount of time it takes for this material to go down by half. So we call it the half time. To say H je skільки часу триває, щоб кількість матеріалу зменшилася наполовину. Розумієш інший? Okay. So we're kind of doing the same thing, but I'm going to introduce a few other ways to use these equations. All right. Go ahead and read question 1. Okay. Underline, circle, write down which variables you have. So I sort of went back to the good old grasp method, right? Like in these kind of questions, you definitely want to follow the model of grasp, where G stands for given. So I just make a list of all the information that is given to me, and I attach it to a variable. R stands for required, right? I put a question mark next to the variable that is required to be solved for. Okay, so I'm given that the half-life is 8 days, and luckily the elapsed time is also given in days. So 50 days passed by. So folks, how many times, before we even do the math, let's think critically about this. If the amount halves every 8 days, how many times, approximately how many times, will the amount have halved? Yeah. How many times, folks? 6, 7, 6, right? Because 8 times 6 is 48. So it will have halved. So it will have halved 6 and a bit more, right? So I could actually do that in my head. I could be like, okay, well, if it was at 200, the first time it halved, it's at 100. The second time it halved, it's at 50. The third time it's halved, it's at 25, right? I could solve this-ish without even doing this proper math equation. Okay, so I just want to estimate. The fourth time, it's going to be 12.5. Fifth time, 6.25. First, second, third, fourth, fifth. So I'm looking for an answer of approximately 3 kilograms. Does that make sense? Yeah, so this is just my estimate. I think my answer is going to be around 3 kilograms. Let's see. I might be completely off. All right. So we need to set up an equation. So we're just plugging stuff into this equation. Go ahead, do that. So AFT, I don't know. Okay, my A naught is 200. No. Oh, right. I want to put the T in here. That's right. Thank you. Right. So it's not AFT, it's A of 50 that I don't know. Beautiful. And then I know that my time is 50 and my halving time is 8. Okay, and now you can get your calculator. Now make sure you're using the calculator you're going to use during the test. The final answer? Oh, don't even do that. What I want you to do, I want you to do the entire thing in your calculator to get the final answer. So 25 over 4. What kind of equal sign are you using? The one with the dot, because we are going to be rounding. That's right. When you're saying, hey, attention, I rounded. So keep one decimal place. How much is it, Mustafa? Where's your calculator? Yeah. Approximately 2.6 kilograms. What does that mean? 2.6 kilograms what? That's right. Left after how many days? 8? 50. Good. Folks, was my estimate beforehand accurate? Like, was it pretty close? Yeah. So now, by having done that, I'm like, oh, yeah, okay, I guess I was I did it twice, and both times I came up with a similar answer. All right, what is B asking us to do? Determine how long it will take. Ooh, I like this one. Get ready. How long will it take until only 12.5% or 1/8 of the iodine remain? I want to show you something. This is a tricky one, but an important one. So I want to know, what is AFT when we have 12.5% of A naught? Now watch this. This is really important. I am not going to input 200 kilograms. I'm going to keep A naught as a variable. And I want you to do that because this will help with other questions. So how do I write 12.5 as a decimal? 0.125. Right? You take a percentage and you divide it by 100. So what I want to know is, at what point will I have 0.125? That's my AFT.
I'm sorry, why did we get 0.125?
Yes, this is the confusing part, right? Let me finish writing the equation so we can see more before we break it down. So what I'm saying is, the amount, the AFT, that I want to solve for is when there's 0.125 of A naught. Now I know A naught is 200, so this would be 25 kilograms. So I could say, hey, when will I have 25 kilograms? But I want to show you an easier way. So all I'm saying is, I actually, in this question, I don't need to know the original amount. I just want to know, how long does it take for me to go down to 1/8 of the original? Folks, how long in this question, let's do some estimation on the side. How long does it take for me to go to 1/2 of the original amount? How did you get that? Okay. After that, how many more days for me to get to 1/4 of the original amount? 16 total, right? Another 8. Okay. How much for me to get to 1/8? Each time I am halving. I'm dividing by 2, dividing by 2. And 1/8 is actually 12.5%. So we know the answer we're looking for. Yeah. Yeah. It's 24. Yes. Very good. Let's discuss that. Right? I doubled 16, but that's not true. The halving time is 8. So after 16, another 8 days for it to half yet again. So I'm looking for an answer of 24. Okay? Now watch this. Look at this equation. Turn to your partner. What do you see that I can do? What can I do that's going to make me so happy? I think I heard it. What did it say? Forget factoring. Easier. What can I do? It's this dance move. It goes like this. What is it? Cancel it out. Right? Actually, I should do the... I don't know. I got to work on that move. It's the double cancel out, right? I can cancel out the A naught. Cancel out A naught. Star. Exclamation mark. Smiley face. Important. Yeah. Thank you. Sebastian found another one of my... That's a big mistake. Anyone else see my big mistake? It was not on purpose. Folks, my big mistake. We're talking half-life, not doubling. I wrote a 2 as the base. It's supposed to be 1/2. Thank you. All right, so do you see how I canceled out the A naught? Do you see that I actually didn't even need to have the original amount? It is, folks, this will be on the test. It will be on the homework. There will be a question where you don't get the original amount. And you're going to say, Miss Sly, you didn't tell us how much there is to start with. And I'm going to say, come on, go back to April 23rd at 11:15, where we had a question where we didn't need to know the original amount because you cancel it out. So anytime you have a question where you are told the percentage of something remaining, you don't need the original amount. All right, so let's see what else we can do. All right, so this 0.125, we actually are going to write it as 1/8. Yeah.
Why did we divide 12.5 by 100?
Because it's percent. You can't write percent in an equation. All right, anyone starting to see what we can do? Yes, can I make 1/8 to have a base of 1/2? What is the exponent? 1/2 times 1/2 is 1 over 4 times 1/2 is 1 over 8. Okay, you could have made the base 2. That would also work. As a result, we can say, oh, 3 equals t over 8. And what does t equal to? 8 times 3 is 24. Hey, that's what we thought it would be. Pardon? You did it a different way? You can. Did you make the base 2? We didn't learn log yet. If you know how to do log, on the test, I need to think about that. Okay? Because I have not taught you log. Yeah. Yeah. All right. Are we good here? All right. Let's do another one. Pharmacokinetics. Ooh. Some of you who might be interested in the medical field, pharmacokinetics is something you could potentially study, something you didn't think existed. So pharmacokinetics is the study of the movement of drugs within the body. That is a whole field of study. Okay? So how long does it take a drug to go all around your body? How long does it take to get out of your body? How effective is it, right? That is all pharmacokinetics. So, and that including the elimination of drugs in the bloodstream. Often it is necessary to know the half-life of a drug in your body in order to determine the dosage, right? So how quickly does the drug leave your body? And that's going to determine how much you initially have to take, okay? And also to make sure you're not taking too much. So, caffeine is a drug. I am drinking coffee. It has caffeine. What does it do? It makes me a bit more awake. But at the end of the day, all that caffeine has left my body, right? And caffeine has a half-life of approximately 5 hours. A cup of coffee has approximately 100 milligrams of caffeine. Generate a function to describe the metabolism of caffeine within the bloodstream. So we've been given the graph here, right? Did you get the graph? Yeah, you did. Did you get the graph? Yeah. All right. So, but let's write the equation of this function. So what do we know about this function? When I drink a cup of coffee, I am given my A naught. What is my A naught? Well, it's 100 milligrams of caffeine. I am also told the half-life. It takes about 5 hours for that caffeine to go down to 50 milligrams. Now that's all I know. Because now I'm going to create a function. Could you have drawn this graph? You could have. What would be, so after 5 hours, how much caffeine is in your body? 50 milligrams. Look here. Oh, that's 10 hours. 5 hours, we're at 50. After another 5 hours, how many milligrams should we be at? 25? Oh, yeah, we're there. After another 5, so 15, we're at 12.5. Right? So you could, in theory, have drawn this graph. Now, let's write the equation. Okay? So if we have, it would be A of T equals 100. That's the original amount. 1/2 is the base. And then a T over 5. Right? So this is just an equation that models the decay of caffeine in your body. So you could use this equation to be like, I want to know how much caffeine I have the next day. I want to know how much caffeine I have after 1 hour. Okay? And then this equation represents this graph, right? Using a graphing application, which could be Desmos, which was done for us, determine when the mass of the remaining caffeine will be 25 milligrams, 10 milligrams, 0 milligrams. So we've been given this graph here, okay? Let's estimate as best as we can. So when do we have 25 milligrams? Okay, so we know that here we have 50 milligrams. Here we have 25 milligrams. How much time has passed? Time equals 10 hours, right? We've halved in by 2. Well, 10 milligrams is not going to fall on a halving time, right? That's not any of the halves. So here we just need to estimate. So 10 milligrams is over here. And if we carefully read this graph as best as we can, 10, 12, 14, 16. I'm going to estimate that time would be 16.5 hours. You might have said something a bit different, maybe 16.8. But do you see how we did that? So we said 10 milligrams. What is the time? Right, so this bottom axis is time in hours, and the top one, the y-axis, is the amount in milligrams. Right, so you could, on your test, be given a graph and have you interpret it. And then, when will the amount be equal to 0 milligrams? What do you think, Greg? How come? So what are you talking about? The asymptote. The asymptote is at y equals 0. So we're saying, in theory, this graph is never going to touch 0. So theoretically, we will never get to 0 milligrams of caffeine. What we're saying is that molecule of caffeine will keep separating and separating and separating. So theoretically, never. But realistically, we know. So approximately, how much time would you say is needed for that caffeine to completely leave your system? What would you say? Maybe 50 hours, right? That would be an estimation, because we know eventually you pee it all out. Like eventually, like what this theory is saying is that even the atom will separate. That won't happen. Eventually, you will just pee out more than half, right? And it will leave. So theoretically, never. Theoretically, never. But in reality, let's just say approximately 50 hours, which is kind of crazy. That's a lot of time to get rid of all the caffeine. Yes?
Like if you have a question like this on the test, you have to write theoretically.
Yes. Yes, definitely. All right, let's look at one more question. Some more fraction work. Doesn't this look like a physics question coming up? The bouncing of a ball. Right? All right, so we have a bouncy ball. And it bounces. And so it's bouncing on a hard floor, which allows it to bounce longer and higher, right? And we know that a ball will never bounce right back to the original height, right? Because some of the energy is transformed into sound energy, into thermal energy, into kinetic energy. Well, no, the kinetic doesn't get lost into, I'd say, thermal, sound. I don't know. Maybe some. Anyway, so some of the energy is lost. So as the ball bounces up, in this case, it only bounces up to 75% of the previous height. Okay, so um, so we need to write the equation. We need to figure out what fraction of the original height does the ball bounce on the sixth bounce, and from what height do you need to drop the ball if you want it to reach 10 feet on the sixth bounce. So before we attack these questions, let's write down, let's try to reason with this. So on the 0th bounce, i.e. when it's starting, what is the height? Well, the height is h naught. Okay, let's just say the original height. So we're not talking original amount, we're talking original height. Okay, after the first bounce, so when it bounces up the first time, how much of the original height will it bounce to? That's right, 0.75%. On the second bounce, it's going to bounce, I need a different color, to 0.75% of the last bounce. Do you see that? Like, this is bounce number 1. And bounce 2 is going to be 75% of bounce 1. So what will the third bounce, how high will the third bounce go? Well, the third bounce is going to be 0.75% of bounce 2, right? And that's going to be the same thing as 0.75 times 0.75 times 0.75 h naught. Do you see how this gets ugly fast? Can I simplify this? So instead of saying 0.75 times blah, 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 for bounce 3, 0.75 to the power of what? 1, 2, 3. Times h naught. Do you see? So every time I multiply 0.75, it's like I'm just adding an exponent. So on the third bounce, it's 0.75 to the power of 3 of the original height. We're seeing this? Okay. Or if I wanted to instead do it in decimal, in fractions, I could say, okay, it's 3/4 to the power of 3 h naught. We good? So using this realization, let's write a general equation. So write an equation that describes the height of the ball after n bounces. So n is the number of bounces. So our height instead of time t, at n, so our height at n bounces is going to be the original height times 3/4 to the power of what?
3. Oh,
N. Right? Okay. So this is different. This is not half-life, but this is another example of decay. Okay, so to what fraction of its original height will the ball have bounced on its sixth bounce? Now, this question you can solve without using this equation, but I want you to. Okay, I want you to solve it using this equation. So what is the height at bounce 6? So that's telling us that n equals 6. Okay, so it's going to be h naught times 3/4 to the power of 6. Oh yeah, let's remember that when I have a fraction, both numerator and denominator get that exponent. So I've got 3 to the power of 6 over 4 to the power of 6. And so I'll punch that in my calculator. 3 to the power of 6 is 729. 4 to the power of 6 is 4,096. H naught. I have no idea what that means. I might have to pop that into my calculator to get a sense that it's 0.178, right? This is actually 17.8%, right? It's approximately 17.8% of the original bounce. So after 6 bounces, it has gone down to about 20% of the original height. The last question says, okay, so on the 6th bounce, I want the ball to go 10 feet high. Okay, so question C says I want h of 6 to be equal to 10 feet. So how high does it originally have to bounce? Well, let's use the work that we've done in question B. Let's say that 10 equals to 729 over 4,096 h naught. Ugly numbers, but it's like, oh, there's only one unknown. I can multiply both sides by 4,096, divide both sides by 729, or some other type of algebra, and I'll get that h naught is going to be 10 times 4,096 divided by 729. I get 56.2, approximate 56.2 meters, feet. What are we talking about? Feet. Yeah. So this kind of question, I think there's a homework question that is similar to this. So return to it, model it. You can stay for lunch, and even if you're like, you know what, I just want to do a couple of these questions for lunch, do that. Questions. Did everyone hear that I have to change, Annabelle? I have to change extra help today at lunch, like right now, as opposed to after school. Yeah.
And we will have tomorrow to school. So.
And